In the last few years, artificial intelligence has evolved at a pace that feels almost cinematic. Models that once required supercomputers to run now fit on your phone. And systems that couldn't understand a simple question just a few years ago now hold coherent conversations, write code, and even reason through complex problems. But behind this rapid progress lies a quiet revolution in how we train these models. A shift from relying solely on massive datasets to a new paradigm where the model itself becomes the teacher. At the heart of this transformation is a technique called self-supervised learning, a method that allows models to learn from raw, unlabeled data by creating their own training signals. Unlike traditional supervised learning, where every input is paired with a correct output, like showing a model thousands of images of cats labeled cat, self-supervised learning doesn't need those labels. Instead, it uses cleverly designed pretext tasks to generate training signals from the data itself. For example, imagine showing a model a sentence with a missing word. The cat sat on the... The model doesn't get told the answer. It has to predict it based on the context. But here's the key. The model isn't being trained to just guess the word. It's learning to understand the structure of language, the relationships between words, and the underlying patterns that make sentences meaningful. That knowledge, once acquired, becomes a powerful foundation for downstream tasks like translation, summarization, or question answering. This approach is especially powerful when applied to massive amounts of unlabeled data, like the entire internet. Instead of waiting for someone to manually annotate billions of text snippets or images, models can learn from the data's own structure. In vision, for instance, a model might be trained to predict what a cropped portion of an image looks like based on the surrounding pixels. Or it might learn to reorder shuffled patches of an image, forcing it to understand spatial relationships and object coherence. The result? A model that learns rich, general-purpose representations, features that capture the essence of language, visual scenes, or audio signals without needing explicit supervision. These representations are so effective that they can be fine-tuned on small, labeled datasets to achieve state-of-the-art performance on specific tasks, often with far fewer examples than traditional methods. But self-supervised learning isn't just about training models more efficiently. It's about enabling them to learn more deeply. By forcing models to infer missing information, predict sequences, or reconstruct inputs, we're not just teaching them to recognize patterns. We're training them to understand structure, causality, and context, core ingredients of intelligence. And this is where things get really interesting. When self-supervised learning is combined with large-scale models and massive computational resources, we see the emergence of capabilities that were previously unimaginable. Consider the rise of transformer-based architectures, models like BERT, GPT, and CLIP, which are all built on self-supervised foundations. These models don't just memorize facts, they develop a kind of latent understanding of the world. Take GPT, for instance. It's trained on vast corpora of text using a simple but powerful pretext task, predicting the next word in a sequence. But because it's trained on such diverse and extensive data, it learns not just grammar and syntax, but also facts, reasoning patterns, and even cultural context. When you ask it to write a poem, debug code, or explain quantum physics, it's not retrieving a stored answer. It's generating a response based on a deep, internalized model of language and meaning. Similarly, CLIP learns to associate images and text by training on billions of image-text pairs, without labels for the images. It learns to understand that a photo of a dog on a beach isn't just a collection of pixels. It's a visual representation of a dog, a beach, and the relationship between them. This enables it to perform zero-shot image classification, identifying objects in images it's never seen before, simply by leveraging the semantic connections it learned during training. What's remarkable is that these models aren't just good at specific tasks. They're generalists. They can handle multiple modalities, text, images, audio, because they learn a shared, high-level representation space where different types of data can be compared and understood together. But this raises a deeper question. What does it mean for a machine to understand something? We don't yet know if these models truly comprehend the world the way humans do. They don't have consciousness or intent, but they do exhibit behaviors that mimic understanding, reasoning, abstraction, generalization. And that's the real breakthrough. We're not building machines that mimic intelligence. We're building systems that acquire intelligence through experience, much like a child learns language by hearing it, not by being told every rule. The future of AI isn't about bigger datasets or faster GPUs. It's about smarter learning. Self-supervised learning is the engine driving this evolution. It's the reason models can now learn from the vast, unstructured sea of human knowledge and turn it into usable intelligence. And as we refine these methods, developing better pretext tasks, more efficient architectures, and better ways to evaluate what models truly learn, we're not just improving AI. We're redefining what it means for a machine to learn. So the next time you interact with an AI that writes, reasons, or creates, remember, it didn't learn from a teacher. It taught itself. And that, more than any single capability, is the most profound achievement of modern AI.